Okay, good. Okay, hi, my name is Litong, a physics researcher at the Institute of Physics, Chinese Academy of Sciences. I'm very, very happy and excited to introduce my project of exploring novel nickelate materials for electronic devices. And could nickel replace silicon? Well, why do scientists all around the world spend lots of time on it? And why did I choose this project? The reason is we are surrounded by electronic devices. And most of modern day electronics contain silicon, the cost of which is low. But nowadays, silicon-based electronics consume a substantial and ever-increasing share of the world's energy, which increases carbon dioxide emissions and leads to climate change. Well, the good news is that some materials have been found that are more complex than silicon, but are promising for the development of electronic devices of tomorrow and that are less electricity hungry. Well, nickels, a type of rare earth oxides, are one of them. Let's take a closer look at what exactly nickels are. Well, nickels are formed from nickel oxide with an addition of an atom belonging to so-called rare earth elements. Well, why do we pay attention to them? Because nickels are known for a special characteristic. They can suddenly switch from an insulating state to that of an electronic conductor if their temperature rises above a certain threshold. And this transition temperature varies according to the composition of the material, which we call metal insulator transition temperature. Well, but questions still remain, however. For example, despite knowing that the material is made of nickel, a rare earth element and oxide, we still don't know how those elements are bound together and how elements react under different conditions. So we all know that properties depend on structures, but which special arrangements and symmetries of the structures impact properties the most is still an open question. Well, so the aim of my research is to use first principle calculations to explore how they are arranged and how their characteristics can be influenced. And with that, let me introduce you to our method of applying force. Yes, the force that we apply on a very, very thin nickel-less film. What is a film? Here, it means a very, very thin layer of material. And the tense strain is analogous to stretching. And compression strain is analogous to squeezing. Well, because the stress and expansion can be made experimentally easily by utilizing different constant lattice substrates, this means that simulation results are practical for researchers in the lab. Well, after simulating nickel-less lattice constants from a compression value of 3% to an expansion and a value of 4%, we have found how the structure of nickelate films is reshaped under various amount of forces. Well, the material in the film doesn't just expand or shrink as evenly as we would think. Actually, it forms an unevenly arrangement called breathing mode. A larger octahedron adjacent to a smaller octahedron, just like our lungs inhaling and exhaling. Well, what about the electrons? We have found that they are arranged by force. The compressing force makes the smaller octahedron obtain more charges, which comes from neighboring oxide 2p orbitals. Yes, they exist like small offices containing more employees, but larger offices holding fewer employers. Just like many PhD students have to share a small office, but our supervisor can enjoy a larger one. Well, in simple terms, I have used an easily usable method, changing the force to manipulate the crystal structures of nickels and adequately describe the arrangement of the orbitals and electrons. And on top of that, my work is contribution to understanding the fundamental structure and characteristics of nickels and the stress and expansion in simulation. If we come across similarity in other systems, the existing results will be valuable. So that's the reason it's very, very useful. And I hope in this way, I can design experiments under various conditions more efficiently without waiting for successful production of materials in reality. Well, and I hope if we are successful, we hope that we can provide the world with more potential functional material options for novel electronic devices, which are more friendly to our environment. Okay, thank you so much for listening. Thank you, I'm Litong. Hope you could like it.